Imagine standing on a world so hot it could melt lead, a world crushed under an atmosphere 90 times heavier than Earth's. Now look up. Through the thick sulfuric acid clouds, a dim light appears on the horizon. But you're not seeing a sunrise, you're seeing the sun, our sun, begin its slow journey across the sky from the west. This is a daily reality on Venus, our celestial neighbor. It's a planet that breaks one of the most fundamental rules we take for granted. On Earth, the sun always rises in the east. It's a rhythm that has governed life for billions of years. But on Venus, the cosmos plays by a different set of rules, challenging our very definition of what a planet should be. This simple yet profound difference is more than just a party trick. It's a clue. A breadcrumb trail leading us back in time to the chaotic birth of our solar system. Why would a planet spin backwards? The other planets, for the most part, follow the same rotational direction as the sun itself, a legacy of the swirling disk of gas and dust from which they were all born. Venus is the exception, the cosmic rebel. Its defiance tells a story of violence, of immense gravitational forces, or of an atmosphere so powerful it can physically move the world beneath it. To understand how strange Venus is, let's first think about what's normal. Picture our solar system as it was forming 4.5 billion years ago. It was a giant spinning cloud of gas and dust. As this cloud collapsed, it spun faster and faster, like an ice skater pulling in their arms. This spin gave everything that formed from it a shared direction of motion. The sun spins this way, the Earth spins this way, Mars, Jupiter, Saturn, they all do. This is called retrograde rotation. It's the default setting for planets in our cosmic neighborhood. It's the direction of the original cosmic dance. Now imagine Venus. It decided to dance to a different tune. While Earth spins counterclockwise, if you look down from above the North Pole, Venus spins clockwise. This is retrograde rotation. It's the planetary equivalent of swimming against the current. If all the planets were cars on a cosmic racetrack, all driving in the same direction, Venus would be the one car slowly, stubbornly, driving the wrong way down the track. This isn't just a minor detail, it's a fundamental violation of the solar system's architectural plan. It begs the question, what could have possibly been powerful enough to make a planet-sized object defy the momentum of its own birth? The consequences of this backward spin are profound. On Earth, our 24-hour day and the direction of our spin create weather patterns, ocean currents, and the very rhythm of life. The sunrise in the east and sunset in the west are baked into our culture, our biology, and our history. On Venus, all of that is reversed. If you think a Monday can drag on, try spending a day on Venus. Time on our sister planet moves at a completely different pace, a pace that would be unrecognizable to us. A single day on Venus, that is, the time it takes for the planet to complete one full rotation on its axis, is 243 Earth days long. Let that sink in. One spin of Venus takes longer than it takes for many planets, including Earth, to complete a significant portion of their journey around the sun. While you are born, grow up, go to school, and start a career on Earth, Venus would not have even completed a few dozen rotations. This incredibly slow spin means that a location on the Venusian surface faces the sun for a tremendously long time. Imagine a day where the sun rises, but then it just hangs in the sky, barely moving for almost 4 Earth months. Then comes an equally long night, a period of darkness and cooling that lasts for another 4 Earth months. This extreme cycle of prolonged heating and prolonged cooling has dramatic effects on the planet. How do you make a planet spin backwards? One of the most compelling and violent theories is the Great Collision Hypothesis. Imagine the early solar system, a chaotic shooting gallery filled with planet-sized objects and smaller protoplanets all jockeying for position. In this tumultuous environment, collisions were not just common, they were world-shaping events. The theory goes that early in its history, Venus was likely spinning correctly, just like Earth. But then, it suffered one or more catastrophic impacts from a massive body, perhaps something as large as Mars or even Earth itself. Picture this cosmic train wreck. A giant object careening through space slams into a young Venus. The impact is so colossal, so earth-shattering that it doesn't just create a crater, it fundamentally alters the planet's rotation. One possibility is that a head-on collision was so powerful that it literally stopped Venus in its tracks and then started it spinning in the opposite direction. The energy required for such a feat is almost unimaginable, an explosion that would make all of humanity's nuclear weapons combined look like a firecracker. It would have melted the entire surface of the planet, creating a global ocean of magma. Another version of this theory suggests a slightly different but equally dramatic scenario. While a giant impact is a dramatic explanation, some scientists favor a more subtle, long-term culprit, the Sun itself. This theory suggests that Venus's backward spin wasn't the result of a sudden catastrophe, but a slow, grinding process that took place over billions of years. It's a story of gravity and friction. In this scenario, Venus was born spinning in the normal prograde direction, but it was always destined for a strange fate due to its powerful neighbor, the Sun, and its own burgeoning heavy atmosphere. The Sun's immense gravity exerts a tidal pull on Venus, just as our moon pulls on Earth's oceans. This gravitational tugging creates a bulge in a planet's mass. On Earth, the moon pulls on our oceans, creating high and low tides. On Venus, the Sun's gravity would have pulled on the solid body of the young planet, creating a slight bulge. As Venus rotated, this bulge would have always been pulled slightly out of alignment by the Sun's gravity. This constant, gentle tug would have acted as a brake, working against the planet's rotation. Over hundreds of millions of years, this solar tidal friction could have been enough to slow Venus's prograde spin down, bringing it closer and closer to a complete stop. But slowing a planet down isn't the same as making it spin backwards. That's where Venus's incredibly thick atmosphere comes in. As the planet's spin slowed to a crawl, the atmospheric tides would have become more influential than the solid body tides. There is a third and perhaps the most alien theory for Venus's bizarre spin. What if the planet's rotation wasn't flipped by a collision or a gravitational tug-of-war, but was instead overpowered by its own atmosphere? This is the atmospheric superrotation theory, and it paints a picture of a world where the sky is in charge. On Venus, the atmosphere is a beast. It's 96% carbon dioxide, incredibly dense, and it moves at astonishing speeds. High in the cloud tops, winds whip around the planet at over 220 miles per hour, circling the entire globe in just 4 to 5 Earth days. This phenomenon is known as superrotation. The atmosphere is lapping the solid planet beneath it more than 50 times for every one slow Venusian day. This isn't just a gentle breeze, it's a massive planet-circling river of gas that carries an enormous amount of momentum. The theory suggests that the friction between this fast-moving atmosphere and the planet's surface, over billions of years, could have acted as a powerful engine. It would have been a constant, relentless force pushing against the direction of the planet's original spin. Imagine a giant heavy ball spinning slowly on a table. Now imagine blowing a powerful, continuous jet of air against its direction of rotation. At first the ball's own momentum would resist, but over time, the relentless force of the air would slow the ball down, bring it to a stop, and eventually start it spinning slowly in the opposite direction. On Venus, the jet of air is its entire atmosphere, a mass of gas so heavy it's more like an ocean than a sky. This constant atmospheric drag, working day and night for eons, could have been the force that reversed Venus's spin. Here is a fact so strange it sounds like science fiction. A day on Venus is longer than a year on Venus. Let's break that down. A year is the time it takes a planet to complete one orbit around the Sun. For Venus, that journey takes about 225 Earth days. A day, as we've discussed, is the time it takes for a planet to spin once on its axis. For Venus, that's 243 Earth days. This means that Venus completes an entire trip around the Sun before it finishes a single rotation. It's a mind-bending concept that completely shatters our Earth-centric understanding of time. What does this actually mean for the planet? Imagine you are standing on the surface of Venus as it begins its year. The Sun is in a certain position in the sky. As Venus moves through its orbit, completing a full circle around the Sun in 225 Earth days, it has still not finished its own daily spin. By the time one Venusian year has passed, the Sun has not even set yet. This creates a bizarre relationship between the planet's seasons, which are minimal due to its lack of axial tilt, and its day-night cycle. The passage of a year is a non-event in the daily life of the planet. This strange temporal rhythm has profound implications. On Earth, our 24-hour day and 365-day year create the familiar cycles of seasons, weather, and life. The fast rotation helps distribute the Sun's energy relatively evenly. But on Venus, the day-year relationship is completely decoupled. Humanity has not ignored this captivating mystery. For decades, we have sent robotic emissaries to peer through Venus's thick clouds and unravel its secrets. Each mission has added a new piece to the puzzle of its strange rotation. The early Soviet Venera and US Mariner missions gave us our first tantalizing glimpses, confirming the hellish surface conditions and the slow, retrograde spin. But it was NASA's Magellan mission in the early 1990s that truly revolutionized our understanding. Using powerful radar, Magellan mapped 98% of the planet's surface, piercing the clouds to reveal a world of volcanoes, mountains, and vast plains. Magellan's incredibly precise measurements allowed scientists to clock the planet's rotation with unprecedented accuracy. More recently, missions from Europe and Japan have continued the investigation. The European Space Agency's Venus Express, which orbited the planet from 2006 to 2014, focused on the atmosphere. Then came Japan's Akatsuki mission, which is still in orbit, and the journey is not over. A new wave of exploration is coming. NASA is sending 2 missions, Veritas and Da Vinci, while ESA is sending Envision. These future explorers will provide even higher resolution maps, analyze the atmospheric composition with incredible detail, and even study the planet's internal structure. So, why do we care so much about which way a planet spins? The mystery of Venus's rotation isn't just a local curiosity. It's a question that has implications for the entire cosmos. Understanding how Venus ended up in its current state helps us refine our models of how planetary systems form and evolve everywhere. When we look out into the galaxy with telescopes like the James Webb Space Telescope, we are finding thousands of exoplanets. Some are gas giants, some are icy worlds, and many are rocky, Earth-sized planets orbiting in their star's habitable zone. We want to know which of these might harbor life. The story of Venus serves as a crucial cautionary tale. Here we have a planet, a twin to Earth in size and composition, that took a radically different path. Its backward, slow spin is tied to the runaway greenhouse effect that turned it into a furnace. Every clue we gather from Venus, from its westward sunrise to its day longer than its year, is another line in the grand cosmic storybook. It's a story that teaches us that a planet is not just a rock in space, it is a complex system, a product of history, chance, and the unyielding laws of physics.